written many outstanding research papers and many outstanding books from which I think all of us have learned. And without much more to say, it's really an honor, a privilege to have David with us. And he's going to talk to us about the theory of free resolutions. Thank you.
Thank you. So is this working? Can you hear well enough? So free resolutions is a subject I've been interested in for a very long time. And I announced that I'd explain about infinite free resolutions. But I think in order to understand how people got there and what sort of things they think about, you have to understand something about finite free resolutions first. This is a subject that really began with David Hilbert. He made his big splash as a beginner in mathematics, roughly speaking the age of some of you, by proving solving one of the major problems of the time. In the 19th century, the late 19th century, the champion subject in algebra was the theory of invariance. So typically people would take polynomials in two variables and look at forms of degree d and let the SL2 act on that space of forms. Think about polynomials on that space of forms and look at the invariance of those polynomials. And people computed those invariants up to all the invariants, and they form a ring, of course. If you have two invariant functions, their product is invariant. So they computed generators and relations for those invariants up to d about 8. And with modern computers, we can, of course, get further. We can get to d equals 9. It's amazing how hard those computations are. And they were extremely clever in doing them. Anyway, the thing that they noticed was that the number of invariants in each degree, the dimension of the space of invariants in each degree, grew as a rational function in D. So piecewise polynomial, if you like, in D. So if you make a generating function, it's a rational function. And they also noticed that the rings were finitely generated. So those were sort of the two big problems of the time, and Hilbert solved them both in a couple of papers. And the basis of the counting argument was the subject of free resolutions. So what Hilbert proved is that if you have a polynomial ring, let's say S is equal to a polynomial ring over your favorite field, in his day it would have been the complex numbers, in some variables, x1 up to xn, and you look at any graded module. He was interested in the graded module of the polynomial ring over the ring of invariance, or the ring of invariance over this polynomial ring. So, for example, you have a homomorphic image, R, and you look at, let's say the kernel is I, and let's suppose for simplicity that I is homogeneous. You have to be more careful and clever if you want to do the general case, but something is true anyway. I is homogeneous, then R becomes a graded module over S, finite dimensional in each degree over K. So you can look at the dimension of R sub D, the subspace generated by forms of degree D. Is this big enough for people to see back there? I have some people at least can see it. Good. And what Hilbert proved was that this function is a polynomial if everything is standard graded, or piecewise polynomial at least if it's not standard graded. There are different ways of saying that. One way is to say that if you take the sum of t to the d times this dimension, then that's the expansion of a rational function. A way that I like better in some ways is to say that these dimensions satisfy a linear recurrence relation. That's completely equivalent to this statement, and it's equivalent to the dimensions being piecewise polynomials in D also, depending on the congruence class of D mod something or other. And the proof is now rather transparent, and here's how Hilbert did it. He said, well, R itself is a homomorphic image of S. And if I choose generators for the ideal I, among other things, he proved the Hilbert basis theorem, which said that I was finitely generated. So he could choose finitely many generators, and they'll have different degrees. So I'll identify them by the degrees. So I'll write summation S of minus d sub I to the power beta 1I. Or maybe I should say beta 1. Maybe this is better notation, beta 1d. So we're stuck with this negative notation. This means S of minus d is the free module generated on one generator in degree plus d. This makes sense because S of minus d sub j, the degree j part, is S in degree j minus d. So that's how you can remember this. But this is something Grothendieck, I think, imposed on us, and it's stuck very firmly. And then you can go on. The kernel of this is also finitely generated. That's the general part of the Hilbert basis theorem. So you can write S of minus d to the beta 2d, let's say, the second stage, and continue, and minus d. And then it's clear that the degree d component here is the degree d component there, minus the degree d component here, plus the degree d component there, and so on. You can take an alternating sum. That won't do you much good, except this comes to an end. So the sums are all finite. So you have finally S of minus d to the beta, whatever it is. Let's say n is always big enough, but it might be less, m n d, let's say. Right. So this reduces the question of whether this has a linear recurrence relation to the questions of whether these do. And of course, S of minus d in degree E is just S in degree E minus d. So it's the same to prove that S itself has a linear recurrence relation. And as you probably all know, the dimension of S in degree d is the binomial coefficient. I said n variables instead of n plus 1. So I have to take n minus 1 here, plus d. Choose n minus 1. So this is a polynomial in d for large enough d, right? When d is negative, this is just 0. So not quite a polynomial, but close enough. So for large d, and this is true when all the generators of S have degree 1. Otherwise, you have to be a little fancier, but not much. So that says that when d is larger, or let's say when e is larger than any of the numbers that appear here, at the very latest, this will be a polynomial function, the dimension of this. So that's Hilbert's argument. And of course, it doesn't really tell you anything about what the function is. It just says it's some polynomial. And the people at the time thought this was terrible, cheating, because previously these theorems had all been proved by actually computing all the invariants and counting. And so they had explicit functions, and Hilbert's theorem, both for finite generation and for the counting argument, were completely existential. So famously, Gordon, who was the king of invariance at the time, said, "This is not mathematics, this is theology." But later on, he came around and said he discovered that theology also has its uses. Basically, he discovered what we would now call Gröbner bases, though certainly Gröbner was not yet born, and Buchberger much less, who named Gröbner bases. But the technique is essentially the same, to look at monomials and prove that it's enough to say something about ideals generated by monomials. So this is the prehistory of the subject. But it's interesting to ask what these complexes actually look like. And I thought, since this is supposed to be a beginning course on this, I should write down at least one or two such complexes explicitly. And it's pretty easy to do. So, in fact, what I'm going to write down goes back to Arthur Cayley, 40 years before Hilbert, though Hilbert doesn't quote Cayley, and it's not clear that he knew that that was the case. But suppose you take a polynomial ring and let's say just two variables and look at the ideal generated by the two variables. So S, and then this will be R, which is S mod X and Y. And then what will come next? Well, of course, there are two generators of this ideal, so I can put here S squared, or better yet, S of minus 1 plus S of minus 1, S squared of minus 1. And this map, if I write a matrix, is X, Y. So now what are the relations between X and Y? Well, they're pretty independent, right? So one way you can get a relation is to multiply X by Y and say that that's equal to Y times X. So just the fact that this is a commutative ring, really nothing else, says that there's a relation with Y and minus X, S of minus 2. Right? So there's a first example of a resolution. Let's write down one more like that just to see that things are not completely trivial. If I took 3 variables instead, I hate writing subscripts, so I'll call them X, Y, Z. Then I can look at, let's call this S. I can look at S mod X comma Y comma Z. And S maps onto that. Obviously 3 generators, so S of cubed of minus 1. Now the relations, now they're still just as independent as before. So the relations are all going to be like this. But there'll be more of them because we have 3 different pairs. So here we have X and Y. Here we'll have 3 relations. One between, X, Y, Z. One between, let's say, Y and Z. So Z times Y minus Y times Z. And 0 times X, that's certainly a relation. And similarly, Z times X and X times Z. And for reasons you'll see in a second, I'll put a minus sign next to the Z. You could put it in either place, and 0 times Y. And then you can say the third one is between X and Y. So I could take Y times X and minus X times Y, like that. Now I wrote this in a skew symmetric form, but why should there be a skew symmetric matrix there? Well, we'll talk about that a little bit. But the advantage of it is that I don't have to think about what to write here. I can just write the transpose of this, and I'm guaranteed that it will compose to 0. So I'll put x, y, z here, right? So, whoops, s. So with degrees, these were degree 1, so I had to shift by -1 here to make this be a degree 0 map. Here I have to shift 1 more to make this be a degree 0 map, so this is -2. And here, again, I have to shift 1 further. That's s of -3. Now, you might well ask, this is all very well, but how do you know that this is exact? Right? How do you know that this is a resolution? Resolutions are defined by saying that each map maps onto the kernel of the previous map. It's clear that their composition is 0, so it maps into the kernel. Why should it map onto the kernel? And one way to see this is to remove all the variables and think that this is really the chain complex of a simplex. That's certainly exact, right? And then you can homogenize it to make this work. That actually can be made into a correct proof. I'll show you a different proof in a moment. So there are 2 actual examples of free resolutions. Now, there are a few terminological things to say. First of all, we chose some relations. Why those relations? I could have chosen this first relation twice, for example. Or I could have chosen this multiplied by x and x. Right? That would still be a relation. This is what's called a minimal free resolution. In the sense, well, you can say that various ways. I chose a minimal number of relations in each case, but it turns out that that's equivalent to saying, in this homogeneous setting at least, that there are no unit elements of the matrices. So this is a minimal free resolution. And one advantage in taking minimal free resolutions is that up to isomorphism, they're unique. That's not so obvious. Why I could have taken, the sum of these 2 relations and the sum of those 2 relations. It looks different, but I can get one from the other by an automorphism of front and back. And so if I take 2 different minimal free resolutions, there'll be an isomorphism between them, not unique in general. And therefore, every feature of this is really a feature of this module, this object. So, for example, I could take the elements of this matrix, x, y, z. Somehow that's an invariant of this. Well, that's pretty stupid. It's clear that x, y, z is an invariant of that. I could take the 2 by 2 minors. If you look at it, I'll get exactly the square of this ideal. So there's nothing new to be seen here, but in other cases there might be. So how can you tell when you have a resolution? Well, for one thing, if I tensored with the quotient field of S, then this would be a sequence of vector spaces, and it had better be an exact sequence of vector spaces. What does that really mean? Each map is mapping into the kernel of the one before, and with vector spaces, it's enough for the dimensions to match, right? So if I have a subspace of another space and they have the same dimension, then they're equal. So one condition for being a resolution, first of all, it should be a complex, which means that the composition of successive maps is 0. And second, the ranks of the maps should add up correctly. So the rank of this is 1, the rank of this is 2. There are obviously non-zero 2 by 2 minors, but if you computed the determinant of this matrix, it would be 0. And you can see that must be true, because when I tensor with the quotient field, this has to have rank 2 because it has to map into the kernel of this rank 1 matrix. So the determinant of this will be 0. And here, well, the rank is 1 again. So let's write down some of those conditions. So suppose I have a complex. So this is a theorem. This was something that I did with David Buchsbaum a long time ago. Suppose that 0, well, F0, let's say, F1, Fn 0 is a complex. That's, in some ways, that's the hardest condition to satisfy because it's equational. These are, if these matrices have high degree entries, then computing the product is not a trivial task, and that should be 0. And the equations that say that's true are complicated equations. However, let's suppose it is a complex. Then let's call it F. F is a resolution, meaning it's exact at every step from F1 on, right? Of course, there will be homology here. You want the homology there because you want to resolve a module, which is the homology at 0, but the rest of the homology should vanish. So F is a resolution, that is to say, hi of F is 0 for all I bigger than 0, if and only if. First of all, the ranks should add up. So let's name these maps. Standard notation is phi1, phi2. So phi is the map coming from fi. So the rank of phi, let's call it ri, satisfies ri plus 1. So that's the rank of the map coming out of fi. The rank of the map going into fi should be equal to the rank of fi. Right? That's the condition that this complex is exact after you tensor with the quotient field. What else should be true? Well, we've identified these ranks, and they play another role. You can look at the ideals of minors of phi of size ri. So let's write that as I sub ri of phi. That's by definition the ideal generated by the ri by ri minors submatrices of phi. Okay? And the condition is that I ri of phi, we could just call it I of phi, is large enough. So what does large enough mean? Well, here, they were all equal to x, y, z. The length of this resolution is 3, and the crucial point actually is that this ideal has codimension 3. And so let's suppose for a moment that, for simplicity, S is the polynomial ring. Then large enough means that the codimension, so this is condition 1, and condition 2 is that the codimension of I sub ri of phi is at least I. If I weren't working over a nice ring like a polynomial ring, then I would call it the depth. And I would replace this by depth, and it would still be true. So that's the state of affairs with resolutions. And it doesn't tell you much about the matrices, except that the ideals of minors are large, but it's enough to get started at least. So let me show you an application, which is something Hilbert already was pleased enough about to put it in his paper. Let's look at the simplest resolutions. Suppose you have, maybe in this situation, we could generalize it a lot, but it's enough to think about it here. Suppose that you're resolving a module R, a ring R, and suppose that the length of the resolution is just 2. So the length, by length I mean this number, n. You might think it should be n plus 1. There are n plus 1 modules here, but by convention, this is length n. So length 2. So what does that mean? There are some ideal here, and there are n generators, f1 up to fn. Any n you like. So you have here Sn. I can wait till this thing disappears. How many relations could you have if the resolution is going to end here? Now, the first condition there tells you that the numbers have to add up. This is clearly rank 1. This should be rank n minus 1, therefore. And if I had more than n minus 1 things here, then the next map would have to have rank whatever the difference was. And there is no next map. That was my hypothesis. So I'm going to say that this ends with Sn minus 1. Okay? So that's the general form of a factor ring with a resolution of length 2. Now, what can we say about it? So the theorem that Hilbert proved, which Lindsay Birch, a student of David Rees, later generalized. So this is called the Hilbert-Birch theorem. This theorem, it's a nice theorem. As I say, Hilbert was pleased enough with it to put in his paper, but it's not such an important theorem that everybody remembered it afterwards. They remembered other things about the paper. And so many other people got to prove it for themselves and be pleased with it. Buchsbaum actually was one of them. Lindsay Birch probably knew Hilbert's work, but other people too along the way have reproven this theorem and been pleased for a while till they realized that it wasn't new. And what it says is that Fi up to a scalar is A times the corresponding n minus 1 by n minus 1 signed minor of this matrix. So I'll write it as delta I. So here delta I is minus 1 to the I times the determinant of the matrix that you get from, this is phi2, this was phi1, the matrix that you get from phi2 by leaving out the ith row. I'll just write I hat here. Okay? So that tells you everything about ideals that you could have of projective dimension 2 like this. So, for example, when would you have such an ideal? Many algebraic curves in P3 have resolutions like this. Not all. These are called Cohen-Macaulay curves, and they have special properties, but many do. If you look at, some of you know about these things, if you look at divisors on a quadric, for example, A divisor on a quadric is defined by two numbers, the degrees of the two projections. A quadric in P3, smooth quadric in P3, is P1 cross P1. So you have two projections of and if you have a curve on it, there might be degree A in that direction, degree B in that. And this form happens exactly when A and B differ by at most 1. So D plus 1, for example. So that's a non-trivial class of interesting examples. So why is it true? Well, let's see, what does the theorem tell us? It tells us that this ideal of minors has to be non-zero. Well, okay, I said it was generated by some F's. I certainly didn't want to put 0 there. So it's of that kind. And phi 2, however, is more interesting. That's supposed to have codimension 2. The ideal of this ideal, the delta i's, codimension 2. Now, you might remember that when you learn how to solve simultaneous equations and lots of unknowns, that you could do it by writing down the determinants of submatrices of the matrix of coefficients. And what you learned was called Cramer's rule, in the United States anyway. And what it says is that if I put here the map delta I instead, then this is a complex. The delta i's are solutions. If you dualize this, there'll be solutions to the dual system of equations. Right? And why is that? That's pretty easy. Here's the matrix. It has n rows and n minus 1 columns. And if I repeat a column, then of course the determinant will be 0. If you compose, starting with the jth element here and compose, it turns out you've computed this determinant for that column being the jth one repeated. So that's why Cramer's rule is true. These are determinants with repeated rows. So that's okay. Now, if we look back at that criterion for being a complex, being a resolution, this has depth 2. This clearly has rank 1. So it satisfies the rank conditions. And they both have depth 2 now. The minors, right? The maximal minors here are just the deltas. The maximal minors here haven't changed. They're also the deltas. So this is a resolution, this top thing. Now, if I dualize this picture, then I could say, here's the delta i's, S, Sn, dual, Sn minus 1, dual, and I can put here phi 1 dual. S. And S dual is S. And I guess I could put a 0 there too. The dual of this map will be an injection because phi 1 wasn't 0. So what do I have? I have something with no homology here. In other words, the delta I maps onto the kernel of this, if indeed it's a resolution. So let's check the conditions for being a resolution. They still have the same ranks they had before. Now I'm using the fact that the delta i's have depth 2, or codimension 2, to say that this is, again, satisfies the condition. So this thing here with a 0 there is a resolution. This is at least a complex. So this maps into the kernel, but the kernel is the image of that. So there's a map here mapping this element of the kernel to this element of the kernel. And since it's a map from S to S, I can write it as a scalar, a multiplication by something. So that shows that the going by A and then the delta i's is the same as phi 1 star, which is exactly this equation. Yeah. So the Hilbert-Birch theorem is an easy consequence of that. And you could try to do this game for length 3 resolutions too. You wouldn't get so far, but people recently have been studying length 3 resolutions very intensely. And it turns out that to do anything similar involves the theory of infinite dimensional Lie algebras. So there are sort of generic forms. If you think about this, what we've written down is a generic form for a matrix like this. Take any matrix phi2, not too trivial, and then write down the delta i's and choose your favorite element A, and you can write down a complex. So we've written down a generic form for this kind of resolution. And you could try to do the same for this situation, length 3, but in general, as I say, the base of that generic form is some infinite dimensional object, which is quite interesting. Anyway, that's current work, which I'm not going to get into. All right, so we've talked about finite resolutions a bit. Let's jump to the infinite case. So Hilbert's theorem applied to polynomial rings. It was generalized by Auslander, Buxbaum, and Sayre in the 50s to the case of what are called regular local rings. So it turns out that the important point about a polynomial ring is actually that the dimension of the ring, the dimension of the affine space, if you like, of which it's the coordinate ring, is the same as the number of variables. That's basically why they behave well. And there's a general theory of local rings in which that's true, where the dimension of the ring is the number of generators, the maximal ideal. Those are called regular local rings, and they're characterized by the fact that every module has a finite resolution, or that the residue field has a finite resolution. And I've written down 2 cases of the resolution of the residue field for you. That's what they always look like. These are called Koszul complexes. So this is the Koszul complex on 2 generators. So you have 2. This is the Koszul complex on 3 generators. And you could obviously have a Koszul complex on n generators, and that will be the minimal free resolution of the residue field over any regular local ring. That characterizes regular local rings too. So that's a happy kind of unclosed system. But what happens when you go beyond that? So if I take a ring which isn't regular, all I have to do is factor out something in the square of the maximal ideal. Then the dimension will go down. The number of generators will not go down of the maximal ideal. So it's got to be non-regular. And the theorem says then that, for example, the residue field, that's what we're resolving here, will have an infinite resolution necessarily. So you could look at what that could look like. So I want to show you a little bit about 2 kind of opposite cases, but maybe first a little bit of history. John Tate was the person who figured out the first of these interesting cases. I don't associate Tate with brutal commutative algebra very much, but rather with class field theory and things like that. And the reason why he was interested is that class field theory involves group cohomology, also in characteristic P. Now, turns out if you have a group algebra in characteristic 0, it's semi-simple. Does everybody know that theorem? Every module is a sum of simple modules. There are just finitely many simple modules. What's so interesting about that? But in characteristic P, it's not true. And it turns out that the group algebra then is not a matrix ring anymore, but it's a product of rings that you can't decompose anymore, called blocks of the group algebra. And each block is associated with a reason why it's nasty in characteristic P, if it is. And the reason it turns out to be an elementary abelian subgroup of the original group that you took. So Tate was interested in resolutions of modules over these elementary abelian subgroups. So what does that mean? Elementary abelian subgroup, let's do the simplest case. Let's say I have Z mod P, direct sum Z mod P, or cross, I guess I should write Z mod P. I'm thinking of the additive group, additive cyclic group. And if I look at the group algebra over in characteristic P, I could write here Z mod P too, but that would maybe be too confusing. So K is the Galois field of P elements, if you like, which of course is just Z mod P as a field. Then this is the kind of ring that Tate was interested in. And of course, if you look at group cohomology, what is it? You perhaps will know it's X'd into X from K, the residue field, into your module. So he wanted to compute things like, so this maps onto K as the trivial module. This is the representation where the generators act trivially. And then group cohomology, HI, if this is the group G, HI of G, or I guess cohomology, I took HI of G with coefficients in anything, is X of I of K with coefficients in that thing. So you can compute this by computing a free resolution of K and homing it into M and taking your chances with the homology. So that's what it is. And the first step, of course, is to know what the free resolution of K looks like. Now, this is maybe a slightly unfamiliar ring, but it's actually very familiar. If you take the generators here, let's say G1 and G2 are the generators, and you look instead at 1 minus G1, for example, then when you take the pth power, because we're in characteristic P, you get 1 to the P, which is 1, minus G1 to the P, which is 1, which is 0. So if you call this element x1 instead, then the equations of this is really the polynomial ring in two variables, modulo x1 to the P and x2 to the P. So this ring is K of x1, x2, mod x1 to the P and x2 to the P. Now, this kind of a ring is called a complete intersection. That just means that the number of elements in the defining ideal is equal to the codimension of that ideal in the ring. In this case, this is an Artinian ring, so the dimension of the polynomial ring is 2, codimension of this is 2, and there are 2 generators, so that makes it a complete intersection. And Tate, while he was at it, wrote down the resolution of the residue field over any complete intersection. And has a very beautiful, simple form. Maybe it's worth writing down one example first. Well, the simplest complete intersection is a hypersurface. Maybe we should start with that. Suppose you had just one of these things. So maybe I have K of X mod X1 to the P. So what's the resolution of K over that ring? Here's R. We could take K as a trivial module over R, and clearly X1 to the X1 is the kernel, right? R. K is this ring mod X, which is X here. What's the kernel of multiplication by X? What annihilates X? Well, if you think for 10 seconds, you see that it's X to the P minus 1, right? And there's nothing else. There's hardly anything else in this poor little ring. So here we have X to the P minus 1. And what's the annihilator of x to the p minus 1? Well, it's x. So this resolution is periodic of period 2. So theorem, maybe I'll prove this for you too. If R is any hypersurface ring, so that means that R is S modulo F, where S is regular, a polynomial ring or a regular local ring. Then every module has a periodic, an eventually periodic resolution of period 1 or 2. And the resolutions have a very simple form also. This is a theorem I proved a long time ago. And here's the simple proof. First of all, this eventually periodic, how do you know why wasn't it periodic right at the beginning like that one? Well, it turns out that as you go back in a resolution, for a while things improve. That's the basis, really, of Hilbert's theorem, too. There we had a finite resolution, and Hilbert's theorem says in n variables, everything stops by this point. So you could say, okay, so the kernel of F1 must be better than the image of F1 in some funny way, or potentially better anyway. And what's true is that the depth of the module goes up. So Auslander and Buxbaum prove that the projective dimension of any module is the difference between the depth of the module, that's the length of the maximal regular sequence on the module. If you don't know what that is, don't worry about it. And the depth of the ring for any module of finite projective dimension. So the depths are going up in this resolution. And that doesn't need regular, it turns out. All it needs is that the depth of the ring is bigger than the depth here. So what happens in any resolution is that as you go back in the resolution, the depths of the modules increase until they get to the depth of the ring. Now that seems like a contradiction here because they didn't increase, it was periodic. That's not very increasing. In this case, the depth of the ring is 0, and so there's no increasing to be done. But in general, what happens is that you resolve back until the depth is equal to the depth of the ring. After that, you don't get any better anyway. And after that, the periodicity sets in. So proof, an apparently special case, which is the general case. Suppose depth m equals depth r. So that's true for the dimension many syzygy of any module. So this is a harmless assumption if you only want to prove eventually periodic. In that case, we can use the Auslander-Buxbaum theorem, thinking of M as a module over the regular ring. And what it says is that the depth plus the projected dimension is the depth of the regular ring, which is the dimension of the regular ring. So in other words, the depth of my module is now 1 less than the depth of S. And so the projective dimension as an S module of this new module M is 1. So we have M, S to something or other, the number of generators, and projective dimension 1. So let's see, the same argument as before says that the kernel has to be Sn again. Right? So that's the resolution of M as an S module. But of course, we wanted the resolution as an R module. So what can we do? We can express the fact that M is an S is an R module. What does that mean? Well, M is annihilated by my equation F. So that means that F times this Sn has to be in the image of this Sn. So I can write that by saying that there's a homotopy, sigma, so that if this is phi1, then sigma phi1 is equal. I guess I first go by sigma and then by phi1, so I should have written it the other way. Phi1 sigma is equal to F times the identity. If you think about it, that implies that sigma phi1 is also equal to F. It's completely symmetric. So, times the identity. So you have these two maps, and now, since their composition is F, when I look mod F, their composition is 0. So I have at least a complex M, R, phi, 1 bar, let's say, R, sigma bar, R, and then since the compositions go both ways, phi 1 bar, etc. In order to make this true, I need F to be a non-zero divisor, which is immediate if S is a regular ring, because regular rings are domains. So that's not a problem. But this would work in general for a non-zero divisor. And so this looks like my periodic resolution, and it is. So what you have to show that if you have, well, that sigma bar, for example, is the kernel of phi bar. So what does that mean? It means if you have a map from some other module with composition 0 here, then it has to factor through sigma bar, right? But if you look at it back here, what does this mean? I have G composed with phi. Let's see, that'll be, I can write that here. So this composition is something times F, maybe A times F. But then I can compose it with sigma and get a new sigma AF or sigma in, yeah, I guess it'll be sigma AF, A sigma F. And that says that I can factor G. Let's see, I have through there. So that will say that I can take sigma times something here and make the factorization through this map, right? This map that I had, which was AF, A is a matrix, of course, is really something that factors through sigma. And that's what this says. So that shows exactness, right? So this gives you the periodic resolutions. Now, Tate did something weaker but stronger. So he does the residue field for any complete intersection, but he doesn't get minimal resolutions for modules. So Tate's theorem says that if you have a complete intersection, R is now S modulo F1 up to Fn, complete intersection, Ci, I'll just say, then the resolution of the residue field, R, K, well, we have something, of course, the Cazul complex is going to be useful because the Cazul complex is at least a complex covering this. It won't be a resolution anymore, but it's a complex. So I have Rn and then wedge 2Rn. If you were watching carefully, you saw that my second map in the Cazul complex I wrote down really depended on pairs of elements. And the right way to write that is to take the exterior square, and so on. So you have a Cazul complex, but then you have more, because if you, here are the x's, x1 up to xn, and now the f's that you had are linear combinations of the x's. So you can write a matrix here, A, let's say, expressing the f's as a linear combination of the x's. There's a different number of these. Let's say there are m of these and n of those. So here we have an Rm, and we can add this. And it turns out that this is for every ring and every residue field. This is the beginning of the minimal resolution of the residue field. But now what to put next? And if we had lots more time, I would work this out for you in general. But it turns out what to put next is to think of this as an algebra. This is a differential graded algebra. The differential in the Cazul complex is actually satisfies the Leibniz rule. So why not make this into an algebra satisfying the Leibniz rule too? And well, these were generators in odd degree, which is why they're supposed to anti-commute. This is wisdom handed to us from the topologists, really. But odd degree generators anti-commute normally, and even degree generators commute. So the natural thing to do would be to take the symmetric algebra on this. And in characteristic 0, that works fine. In characteristic P, it turns out that you forgot that the exterior algebra had divided powers. This is really an anti-commutative divided power algebra. And so you take the divided power algebra here. The divided power algebra, in case you've never seen it before, of Rm, you can define it as the dual of the symmetric algebra of Rm. Dual. Graded dual. So, no matter. This is some other algebra very close to, which is equal to the isomorphic to the symmetric algebra in characteristic 0, and otherwise has some extra elements in it. So it turns out that the minimal free resolution of K is some complex that you make out of the Cazul complex on n generators, tensored with the divided power algebra on m generators. Now, people were very excited about this, of course. It's obvious that you could do this in very general setting, right? You could say, okay, I started with the Cazul complex. Unfortunately, it wasn't exact here. So I put in some more relations. And just to make nice, I made them into an algebra. Well, now suppose it's not exact here, which will be the case if it's not a complete intersection. Let's just put in some more generators of the next degree and continue. And now we have a complex. This really works. Unfortunately, it's very hard to understand what you got. So it's now known that except in the complete intersection case, you have to add new generators in every single degree. And the number of generators is more or less up for grabs. Nobody has any formula for the number of generators you need to add beyond this first step. So you get, it's also a crazy thing to do because in exchange for fixing one homology group, you've added typically infinitely much stuff to the resolution. So it's absolutely amazing to me, the theorem of Gullikson, which says that this is always a minimal free resolution if you do it minimally at each step. So people really struggled to figure this out. These are called the deviations, the number of elements you have to add at each step. and but nobody ever made much sense of them. So that's the case of a complete intersection and what came from it. Let's look at the most opposite kind of example. Complete intersections are wonderful, but they are not typical, right? Almost nothing is a complete intersection. It's just pure luck when you find one. So you have to look at other things too. So let's see what happens if I take R to be the first non-complete intersection ring, I think, which would be K of xy modulo, not x squared and y squared, but x squared, xy, and y squared. Okay? That's a very innocent little ring. Let's see what its resolution looks like. So again, we can take the residue field. By the way, you can do this for other modules. I should have said that maybe. So the paper in which I published this hypersurface case, I tried to do the general complete intersection case. And you can again write down a resolution for an arbitrary module, but it's usually not minimal. In this case, we could get a minimal resolution. And so not minimal resolutions are a lot less interesting than minimal ones because they're not so rigid. They don't really represent the module so clearly. By the way, that's one of the weaknesses of the derived category, is you can't tell a non-minimal resolution from a minimal resolution. And yet the minimal resolution has a lot more information in it. So that's a problem that people worry about. Anyway, what's the resolution here? So we have R, obviously, and we could take the Cazul complex again, R2, X, Y. Here we have Y and minus X. But if you think about it, there are lots more equations because X squared is 0, Y squared is 0, and XY is 0. So it's probably simpler to write this as, forget that one, and write X 0. That'll be a relation, right? X squared is 0. 0x is a relation too. Y, 0y, and y 0. These are all relations. 4 relations. Why 4? Well, if you think about this, what this is, you have degree 0, k, degree 1, x and y, and nothing else. So the maximal ideal, which is what the image of this is actually a direct sum of 2 copies of k. So the first syzygy, as it's called, here is k plus k. Now, here you resolved k. Now you're resolving k plus k. It must be the direct sum of 2 copies of the resolution of k. Right? So that's why we got 4 here. And guess what? The image of this, well, it's in the maximal ideal times this. The maximal ideal is 2 copies of the maximal ideal. There were k plus k before. Now we have 4 k's. And so we're going to get the tensor algebra. Right? The minimal resolution is the tensor algebra instead of the divided power algebra. This is a nice, at least in characteristic 0, this is the dual of in the complete intersection case, the dual of a finitely generated algebra. The symmetry, basically a commutative algebra, except for this very slight non-commutativity. In this case, it's a tensor algebra, wildly non-commutative algebra, as non-commutative as they get. So here, one way to write this is to think in the following way. If I resolve this over k of xy, let's call this S as usual, then this has resolution S. There are 3 generators of the ideal. And you know what's going to come next because we saw the Hilbert-Birch theorem. So it's S2. And here, what we're really getting is the Cazul complex, which would be 1, 2, 1, tensored with the free algebra on S2. So the minimal resolution is the Cazul complex, wedge of R2, tensored with the free algebra, I'll write it as the tensor algebra, on S2, if you think of this as the resolution F, so this would be F1 and F2. This is the free algebra on F2. Turns out that's a typical pattern too. And that's the pattern typical of what are called Golod rings. So if you resolve your ring R and chop off the first term, then you can always make a resolution of the residue field based on the tensor algebra on the rest of the resolution, tensored with the Cazul complex. And there are even generalizations of that. You could take a resolution of R as an S module and a resolution of any module as an S module, and then the truncated resolution of the ring, the tensor power of the truncated resolution of the ring, tensored with the resolution, whatever it was, of the module, will be the basis for a probably non-minimal resolution of the module. So there is a kind of closed formula for these infinite resolutions. And this has a big advantage over this construction, which also can be generalized a bit, because this construction depends on infinitely many choices. But this construction, it turns out, depends on only finitely many. So this is a sort of holy grail, I think, is to write down the minimal resolution of a module in terms of finite data. So here is a non-minimal resolution you can write down in terms of finite data. Let me write it more precisely. So this is, many people have improved this to the point of this last version, but this is a theorem of Jesse Burke, which says that if you have a regular ring S, actually more general than that, but never mind, and a ring R, which is an S algebra, let's say R is S mod I, and you look at the resolution of R, S, F1, etc., and you look at the resolution of any module as an S module, so M is supposed to be an R module, but I'll consider it as an S module, S to the, well, let's call it G0, G1, etc. These are finite resolutions. Then there are some maps called an A infinity structure. It starts with the differentials. So first of all, what's an A infinity algebra on this resolution? You have the differentials. Good. It's a differential graded something or other. Then there's a natural multiplication on such a resolution because R tensor R is just R. So if you take the tensor product of this resolution with itself, that's a non-minimal non-resolution. That's a complex over R tensor R. So it maps to the resolution of R tensor R, which is R. So that's a multiplicative structure on this complex. Now, you can make it commutative if you want, but don't bother because it's not associative, almost never associative. However, it's associative up to homotopy. And anyone who studied topology will know what comes next. The homotopies are well behaved up to homotopy, and so on forever, except that because these resolutions are finite, the forever is just finite. So there are finitely many maps called the A infinity algebra structure on this resolution, starting with the differential and the ordinary multiplication, and then the homotopy for associativity and so on. Finitely many. Very easy to write down. The machine will do it for you in the twinkling of an eye. Now, if you have an A infinity algebra structure, you might hope you get an A infinity module structure, whatever that is, and indeed that works. So, as the corresponding structure of A infinity. Module here, for the same reason that we had an algebra structure here, there's a natural map from F1 tensor F to G0 to G1. In fact, we saw that map acting already over here, this is really F1, the resolution of the F's tensored with G0, which is R. So in the same way, you get a map from F1 tensor G0 into G1, and then you can continue fixing associativity as you go, basically. So you get an A infinity module structure here. Again, that's just finitely many maps, despite the name, and the machine will write it down for you. And in terms of that, you get an explicit infinite resolution of the module as an R module, which is sometimes minimal, tantalizing. So it turns out that if you start with a ring for which the residue field resolution is minimal, like this one, then every module has a syzygy such that this resolution is minimal, just like the eventually periodic situation. In fact, these hypersurface rings are the unique intersection of the class of complete intersections with Golod rings. Hypersurface rings are also Golod rings, as well as complete intersection rings. So this all fits together in that way, and in that case, you would get the periodic resolutions eventually. I could go on. Let me speculate a little bit rather than trying to tell you more theorems. I would have supposed, out of the starting gate, that the sort of normal behavior of these syzygy modules. So a syzygy module is just the kernel of one of the maps in the resolution. And if you take a minimal resolution, then I would have expected that the syzygy modules would more or less always be indecomposable modules. Why would I expect that? Well, there's a class of rings for which it's true, that helps. And basically that class of rings is a generalization of the complete intersection rings called Gorenstein rings. So for Gorenstein rings, that's the normal behavior. What I said is not quite true as I said it, but very close. But it turns out that for Golod rings, more or less the opposite is true, at least for the residue field. And just a few years ago, these resolutions of Golod rings, residue field, by the way, that's what's due to Golod, is the case of the residue field. When the, I didn't state Golod's theorem, but it turns out that when the ranks in the resolution match this pattern, then this idea gives you a minimal resolution of the residue field, though not generally of other modules, until you take syzygies. So those are called Golod rings for that reason, and he was the one who figured that out. And the first person who made an infinite resolution explicit is certainly Tate. Golod was almost immediately afterwards and figured out this pattern for the residue field for Golod rings, and it's now been generalized and generalized, so we have it in a very general situation. In both those cases, the ranks of the modules are, again, satisfy a linear recursion. That's called the conjecture about Poincare series. That's a conjecture that Kaplansky made. Sayre stated as an open problem. Naturally, with those two people behind it, everybody was interested. But there's a political story there, too. Maybe I should tell. Jan-Erik Roos, when he was a young man, he's dead now, was in Sweden. And at that time, Swedish mathematics was almost entirely partial differential operators. Hermander and his immensely powerful school ruled the roost, and there was basically no algebra. And Roos was an algebraist, and he wanted to change that. So he plotted very consciously, and he told me his plot before it was executed, so I know this is true, to make a school of algebra. And he decided that the way to do that, to break into this clique, was to pick a problem and gather a group of people around him to solve that problem. And the problem he picked was the problem of whether the ranks in a minimal free resolution of the residue field always satisfy linear recursion. And they do very often. many, many beautiful theorems were proven about cases where they do. And then David Annick realized that an example from topology was a couldn't be used to make a counterexample. And so the house of cards collapsed in some sense. People still go on proving that in special cases this is true, but the wind went out of the sails a little bit. The School of Algebra, however, survived, is still happy in Sweden, nicely. Anyway, I think it's more interesting now to look at syzygy modules and ask what you can say about them. For example, do they decompose? So here's a theorem that Heilong Dao and I proved. If you have a ring, and if the residue field appears as a syzygy in the second syzygy, then it will appear in every further syzygy as a summand. So these are called Sockle summands. So, theorem. If K is a summand, let me write it this way, of sys 2 of K, then it's obvious then that K is a summand of every even syzygy, but in fact it's a summand of every syzygy. K is a summand of sys I, K, or all I bigger than or equal to 2. So these are called Birch rings, and you can characterize them. In order for this to happen, of course, the ring has to have depth 0. Otherwise, K couldn't be a summand because it has depth 0. So, but you can always reduce to that case. You take the module, you resolve for a while till it has maximal depth, and you factor out a regular sequence, and you get down to a depth 0 ring and a depth 0 module. So this is a fairly innocuous kind of assumption. It turns out there's something called the Birch index. This is the case of Birch index 1. If the Birch index is at least 2, then K appears as a summand of every module eventually. So that's, and in fact, the optimal bound is 5. So it appears in the 5th syzygy of every module. Rather surprising that a number like that should appear. Anyway, this is work with Heilong Dao. So summands. Well, it turns out if you take a Golod ring and resolve the residue field, for some reason Golod didn't notice this, although it's very easy from what he did. Every syzygy after the number of generators of the ring is a sum of previous syzygies. So that, again, that's a reason why there's a linear recursion. That's enough, more than enough to make a linear recursion. But it's a much, much stronger reason, right? It really decomposes every syzygy. Once you get to that stage, you know every syzygy module in closed form. So that happens for all Golod rings. That's not very common, but here's a conjecture of this kind. It turns out that if you have a Golod ring, then K of depth 0, then K will appear at the latest at the dimension of the ring, +1. And it seems to appear, it can skip 1, but then it appears ever after. That's a theorem. But now what seems to be true is that with the exception of that pattern, skipping 1 and then everything, if K ever appears in the resolution of the residue field of any ring, it appears ever after. Of course, if it appears in the 10th syzygy, then it appears in the 20th syzygy, etc. But in fact, it seems to be a continuous track of syzygies in which it appears. That's a speculation. Another speculation is that if you, of course, looking at maximal minors like the way we did for finite resolution is a fool's game for the general case because the depth of the ring is probably 0 to begin with. And so the minors might be 0 or not 0. There's no such thing as the rank of the map. It's just a dead loss. But you can still look at the entries of the matrix. And if you I was going to do this as a magic trick, ask someone in the audience to pick a ring and resolve the residue field. If you look at the ideal of entries, the ideal generated by the entries of the ith map, it almost always becomes constant after a few steps. I have no idea why that's true. Sometimes it's periodic period 2, for instance, in the hypersurface ring case, but periodic or constant. There are counterexamples, but very, very special. And so something like that must be true in general. You can think about adding up the first n syzygies and see if that stabilizes, for example, first n ideals. So that's another sort of structural speculation about infinite resolutions. And I think that's really the future of the subject, not the number of generators of the nth module, but the structure of the nth matrix. And that's what it should be by analogy with a finite case, where the structure of those matrices was paramount. Anyway, that's, for what it's worth, an introduction to this funny subject. Thanks for listening.
Thank you, David. Very great talk. Questions, comments? No? Yes, please.
Well, thanks for the talk. Is there no regular rings that has a? Is there a no regular ring that has a minimal resolution?
So every module over every local ring has a minimal resolution. Question is whether you can construct it. So minimal resolution just means that you map a free module onto your ring, you choose a minimal number of generators. That's well defined over local rings, not over global rings. But local or graded rings, you can always have a good notion of minimal number of generators because of Nakayama's lemma works, basically. This is an application of Nakayama's lemma, if you know that. Then you get some kernel, and you take a minimal set of generators of the kernel and use that to map a free module onto the kernel and continue. And that is a minimal resolution. So we can always construct step by step a minimal resolution. But finally, we're constructing something that depended only on finitely much data. The equations of the ring, they have finitely many coefficients. The equations of the module, there's a matrix with finitely many coefficients. There ought to be, well, ought is a funny word in mathematics, but maybe there is some kind of formula that lets you think what the nth object should be, the nth syzygy map should be in terms of that finite set of data. Is it semi-continuous in some way? You know, what are the parameters? Even the question of what rings are goal-led, this is some condition on the ideal that's finitely many coefficients. I don't know actually whether that's a closed set, an open set, or what I would expect a locally closed set of ideals in, let's say, in the Hilbert scheme. So many mysteries of that kind. But there are always minimal resolutions, just a matter of our not knowing what they are. Ignorance.
Thank you.
More questions? There's one.
Ah, yes. I'm listening.
Oh, hi. So can you hear me?
Too loud, but yes.
Oh, sorry. Is Annick's counterexample related to, or maybe even the same as, his counterexample showing that there are simply connected finite CW complexes such that the Poincare series of the homology of the loop space is not a rational function?
Yes, very closely related. You can't go instantly from one to the other, but that's the basis of the idea that he had.
Thanks.
More comments, questions?
Well, once I know that we can ask, can you hear me?
Jan Erik Roos, of course, reacted to this counterexample in a positive way. He found lots of other counterexamples and understood a bit how to construct them.
Can you hear me? Probably not. All right.
Yes, we hear you.
Oh, I'm sorry. So quick question out of the comment you just made. So do you have a way to extract a subcomplex of the minimal free? If I think of each factor that you're extracting in the infinite minimal free resolution,
I couldn't understand the words.
So what I'm saying is that if I understood correctly, you are extracting a subcomplex out of the minimal free resolution with the last comment that you made.
Did you understand that?
Can you repeat it, speaking a little more en voz más alta?
So how about that? So I can send an email. I can better send an email. I'm sorry. Thank you.
Sorry. Maybe the following is the answer to your question, which I didn't understand. If you take any resolution, then the minimal free resolution is a direct summand. And the minimal free resolution is unique, up to isomorphism, though not unique canonically. So in some sense, I'm looking for a subcomplex always of this non-minimal resolution. But it seems to be hard to make it that explicit.
Well, I have a question. I know that theorem is very beautiful. That if you have S regular and then you have a hypersurface,
Yes.
then every module has an eventually periodic resolution of
Yes.
period at least two. So
At most two,
to
right?
me, surprising and very beautiful. Is there an extension or something for complete intersections?
Yes. So there's a generalization for complete intersections, which gives you a closed form resolution, which, however, has to grow, right? It can't be periodic. As soon as the effective codimension is more than one, it will grow as a polynomial of degree one less than that codimension. And you construct it again by taking a divided power algebra tensored with the resolution of the module over the regular ring. So all that is true and very explicit, but again, it's a non-minimal, typically a non-minimal resolution. If you want a minimal resolution, you can get that for a price. So it turns out that if you take a sufficiently high syzygy, and we can talk about what sufficiently high means in that context, if you take a sufficiently high syzygy, then there is a kind of closed form minimal resolution. And this was worked out by Irena Payeva and me a few years ago. The nicest form of our theorem is called layered free resolutions, and you could find it online in the archive, for instance. But unfortunately, what does sufficiently high mean? It's the regularity of an Ext module over some ring, over a certain polynomial ring. And the Ext module can have any regularity it wants. So there's no it's a finite number, finite computable number, but it's not, there's no universal bound. It could be very large. Yeah, so that's the best I know. Yeah.
Any other comment or question? Okay, if not, then let us thank the speaker.
Yeah. Mm.
And really, on behalf of all of us, David, thank you very much for having come to Mexico, to Cuernavaca. It's very, very exciting for us, very encouraging, very inspiring. Thank you.